Hi, I'm Abranil. Welcome to my talk on black box identity testing of non-commutative rational formulas in deterministic quasi-polynomial time. It is joint work with V. Arvind and Partham Mukhopadhyay. The plan of the talk is as follows. I'll start by defining what is this rational identity testing problem is. Then I'll present our result followed by a brief overview of our approach. Finally, I will conclude with some interesting open problems. So let's start by defining what is this rational identity testing problem. So we'll look at each term one by one. So the term rational comes from the use of inverse gates. In general, in arithmetic circuit complexity, we use additions and multiplications as basic arithmetic operations to compute a multivariate polynomial. If you allow inverse gates in the commutative case, it now computes a rational function in the function. As you know, a rational function can be expressed as like a ratio of two commutative polynomials. It admits canonical representation. Indeed, it was shown by Strassen that given any polynomial size commutative rational formula, you can actually represent it as ratio of two polynomial size commutative formulas. In other words, given any polynomial size commutative rational formula, it doesn't matter how many inverse gates you have, you can push all the inverse gates to the top of the formula with including only polynomial block in the side. However, in the non-commutative case, where the variables don't commute, we treat the strings as non-commutative monomials. Then, if you allow inverse gates in the computation, it becomes quite complicated. It computes non-commutative rational function in the free skew field. These objects are extensively studied in mathematics. One can think of free skew field as like the smallest field containing the free algebra, the non-commutative polynomial ring. For this talk, it suffices to consider the free skew field containing the non-commutative rational functions, where we define non-commutative rational functions as like two non-commutative rational formulas computing the same rational function if they agree on every matrix substitution. But one should note that a rational formula may not be defined on some matrix substitutions. So when we say that two rational formulas, they agree on every matrix substitution, what we mean that they must agree on every matrix substitution whenever both of them are defined. Unlike the commutative case, we can't push all the inverse gates to the top for non-commutative rational formulas. So the number of nested inverses from leaf to root path, the maximum number of nested inverses, it shows how complicated a rational formula is, a non-commutative rational formula is. And this is characterized by the inversion height of a non-commutative rational formula. For example, this is an example of inversion height 2 rational formula. Okay. Let us now move to identity testing part. So the polynomial identity testing, or the PID problem, most of you are aware of that. Given a succinct representation of a multivariate polynomial, the problem is to decide whether it is computing a zero polynomial or not. In commutative setting, it admits a randomized polynomial time algorithm, and de-randomization of this problem is one of the most interesting open problems in theoretical computer science. The PID problem is of two types, white box and black box. In white box, we can see how the polynomial is being computed. In black box PID, the polynomial is actually given to us as an evaluation oracle, where the goal is to decide if there exists a non-zero evaluation where we can only query the oracle. An important notion regarding this black box PID is this notion of hitting set. A hitting set is just a list of evaluations. So a hitting set H for a circuit class C, it is defined as follows, like for every non-zero polynomial in the circuit class, there must be one non-zero evaluation in that list, in that hitting set H. Okay. So now move to non-commutative PID, but the question is same. We want to test whether it is a zero polynomial or not, but this time it is over the free algebra we want to test. How different it can be from the commutative setting? just follows from this simple example. X plus y into x minus y is equal to x square minus y square, but it is only in the commutative setting. This doesn't hold in the non-commutative setting. As x, y, and yx, we will treat them as two different monomials and they are not going to cancel out each other. As we have said that for black box case, our goal is to come up with some witness of non-zeroness. But here, any field substitution will not serve as a witness because it doesn't respect non-commutativity. So we come up with matrix evaluations which respect this non-commutativity. And also we want these matrices of small dimension to do the evaluation efficiently. So here, the notion of fitting set is a list of matrix evaluations such that for every non-zero polynomial in the circuit class C, there will be a non-zero matrix tuple in our heading set H. Interestingly, unlike commutative settings such as heating set, a quasi-polynomial such efficient heating set construction is known for non-commutative formulas, more generally for non-commutative algebraic branching programs. Okay. Now we are ready to define the rational existing problem. So given a non-commutative rational formula, we want to decide if it computes the zero function in the free skew field. Recall that from the semantic definition of rational function, what you want to test, that does it exist a non-zero matrix substitution or this non-commutative rational formula? Consider this example, which is famously known as was identity. It is actually a rational identity. You can check that for every matrix substitution, it is actually zero. So you can guess the non-triviality, the difficulty for this problem comes from the fact that it doesn't have any canonical representation. Consider the commutative rational interesting problem. It is not that interesting because of the canonical representation. We can just reduce it to commutative formula PID. But the non-commutative rational formula, we can't express it as like a ratio of two non-commutative polynomials, non-commutative formulas. We can't expand it term by term also. This lack of canonical representation makes this problem really difficult. So the previous approaches, what it does to attack this problem, they solve a more general problem, what is known as non-commutative singular problem. Let us first define the commutative counterpart of this problem, which you might be more aware of. So given a linear matrix, the commutative singular problem asks that whether this matrix is invertible or not in the function field. Equivalently, we want to find some substitution such that if you evaluate the linear matrix on that substitution, the determinant of that evaluation will be non-zero. Similarly, in the non-commutative singular problem, we want to test whether that linear matrix is invertible or not, but this time we want to test it with the free skew field. And the equivalent definition is that we want to decide does there exist some matrix tuple P1 to Pn such that if we evaluate each entry, if we blow up each entry by evaluating on that matrix tuple, then consider the blown up matrix and check the determinant of that blown up matrix, whether it is zero or non-zero. This is the non-commutative singular problem. So the connection of the RIT problem comes from the fact that a non-commutative rational formula phi of psi j's is non-zero in the free skew field, even only if a linear matrix L of psi at most 2s is invertible over the free skew field. In other words, RIT reduces to this non-commutative singular problem. So what is known about this problem? In white box case, where we can see how the problem is being, how the formula is being computed, we have a deterministic polynomial time algorithm due to the work of Karl, Gurvitsen, Oliveira, and Wigderson that works over rational. Then it was extended over finite fields due to Ivanas, Shah, and Subramaniam. And there was another algorithm, new algorithm based on convex optimization due to Hamada and Hirai. The problem can be solved also in randomized NC, that is parallel algorithm, randomized NC due to Darcy and Markham. So it is presented as a randomized polynomial time algorithm, but we observe that actually a rational formula can be evaluated on any matrix substitution in NC that puts the algorithm in randomized NC time. Whereas in black box, we can do randomized polynomial time algorithm. This is the best for, this was known as the best one for the general rational formula, follows from the same paper of Darcy and Markham. Okay. So one should note that all these results also hold for non-commutative singular also. Okay. So now we are ready to present our result. What we show for any invariant non-commutative rational formulas of sizes. Consider any formula which is of sizes and suppose the inversion height is theta. Then we can construct a heating set, a list of matrix tuples of size ns power theta power order 1 log square ns in the same running time, where the dimension of the matrix of the heating set, it is like ns power theta power order 1. Okay. Now recall that we said earlier that we can't, in non-commutative formulas, we can't push the inverse gates to the top. However, what we can do, we can actually rebalance the formula and we can control the inversion height somewhat. So it is exactly what was shown by Lewis and Wigderson, that without loss of generality, a rational formula of sizes has the inversion height bounded by order log s. So we are a bit sloppy here. What we mean is that for any rational formula sizes, there is an equivalent rational formula of sizes. By equivalent, what you mean that it is completing the same rational function and it is defined on same matrix substitutions. Moreover, the inversion rate of the second formula is bounded by order log. So what it tells us that without loss of generality, one can think of theta is bounded by order log s. Now putting the value of theta as order log s, what do we get? That in black box setting, the RIT problem can be solved in deterministic quasi-polynomial time. That is, we can give a quasi-polynomial length list of matrix tuples such that for every rational formula of sizes, if there is some matrix evaluation, some non-zero matrix evaluation, then one will be able to find that non-zero matrix evaluation in that list of matrix tuples. Okay. Also, we improve the parallel complexity and we show that rational testing problem is in quasi-NC. Here we also use the observation that a rational formula on a polynomial matrix substitution can be evaluated in NC. So where exactly our result fits? In white box case, we actually improve the parallel complexity of the rational testing problem. From randomized NC, we de-randomize it, we obtain the first deterministic quasi-NC algorithm. Whereas in black box case, we obtain a deterministic quasi-polynomial time algorithm. However, it is important to note that our result only holds for rational identity testing. It doesn't hold for non-commutative singular. Okay. So for the remaining time, I'll now present our proof idea. So our approach is motivated by this simple observation that follows from the definition of any rational formula of phi theta, that a rational formula phi of phi theta can be thought of as the composition of a non-commutative polynomial expression, actually non-commutative formula, if over x1 to xn and y1 to ym, where all these y1 to ym are replaced by inverses of phi1, phi2 up to phi where each phi is a rational formula of height theta minus 1. So any height theta formula is a composition of a polynomial and inverse of height formula of height theta minus 1. Moreover, if that formula is of size S, then all these subformulas of height theta minus 1 are also of size S. Okay. Note that a rational formula phi is not always defined. Simply, if you take any matrix tuple where phi1 is an identity, then when you'll be able to take the inverse, it will not be defined. Therefore, phi will not be defined. We consider a special case where a matrix tuple P1 to Pn is given to us for free, such that phi is defined on P1 to Pn. Again, notice that phi is not always defined. Here it is given to us for free. In that case, what we see, we revisit the reduction from rational testing to non-commutative singular. If we have such a matrix tuple P1 to Pn, for that corresponding linear matrix L, suppose that linear matrix L is of size S. If you look at the top left submatrix of size S minus 1, call it L1, that L1 will be invertible on that matrix tuple P1 to Pn. Moreover, we can test non-commutative singular in black box with that special property that the top left corner, we have a matrix tuple on which the top left corner is invertible. Then we can reduce this problem to PIT of non-commutative AFs, which can be solved in black box. So, if we are given a point of definition for a rational formula, we could have solved this black box identity testing algorithm efficiently in quasi-polynomial time. Okay. However, we don't have that promise. So we want to construct a matrix tuple for which a rational formula will be defined. So our idea is to inductively build a heating set for every height for rational formulas of each inversion height. So consider the base case where theta equals 0, where you don't have any inverse gates. So this is exactly the non-commutative formula for which you already have a force-split heating set. But the difficulty is that a rational formula of height theta may not be defined on a heating set for height theta minus 1. Why? Consider this case. So suppose there is some matrix tuple P1 to Pn where Phi1 to Pm, all of them are defined. All of them are non-zero. But heating set only guarantees that they are non-zero. It may happen that P1 to Pn is non-zero, but it is not invertible. Therefore, when you are computing this P1 inverse, it is not defined, and therefore P at P1 to Pn will not be defined. To tackle this problem, what we do, we strengthen our inductive hypothesis. We come up with this notion of division algebra heating set, where all the matrices in our heating set are inside a division algebra. And we do this for every inversion height. So what is the division algebra? A division algebra is just a matrix algebra, sub-algebra, where for every non-zero matrix, you can add, you can subtract, take product, take inverse. Whenever it is non-zero, it will be invertible. In other words, suppose if you construct a division algebra heating set for height theta minus 1, then you know that any formula of height theta, if all its subformulas are non-zero on some point of the division algebra heating set, that formula of height theta will also be defined on that point. Okay. So we go over the base case again. Here we need to modify the flow-split heating set. We construct a division algebra heating set for non-commutative formulas. And the idea is that we actually embed the flow-split heating set inside a cyclic division algebra. So I'm not going to define what is the cyclic division algebra. It is a special kind of cyclic division algebra that has some nice shape that is crucially exploited in our result. Okay. Finally, we use this inductive step where we show that this construction of division algebra heating set for height theta, given a division algebra heating set for height theta minus 1, it reduces to certain division algebra heating set construction for non-commutative ABPs. Okay, so now we can put everything in a flowchart. In the base layer, we have division algebra heating set for arbitrary non-commutative AFPs. Invariant non-commutative AVP of with R of D many layers, and also we crucially use a special prime P such that the dimension of the matrices of the heating set is some power of P. So why do we need that? We're coming to that. So when we want to construct a heating set for invariant sizes theta inversion height rational formula phi, given a d theta minus 1 heating set of phi hat ns theta minus 1, what do? We actually reduce this problem to division algebra construction of non-commutative AFP, where the number of variables, number of size of the width, number of layers, everything gets increased depending on the index of that d theta minus 1, the size of the matrices in that heating in the division algebra d theta minus 1. Finally, the division algebra d theta will be a tensor product of these two division algebra d theta minus 1 and d0. In general, this tensor product may not produce another division algebra. To ensure that it is again a division algebra, what we do that the dimension of the d0 heating set, we make it relatively prime from the dimension of d theta minus 1 heating set. From the theorem of Pierce, it shows that the final thing will again be a division algebra. To tackle this dependency on this L theta minus 1, so we need to take care of these parameters separately. We need to do a finer analysis of all those parameters. I'm not going into all those details, so please check our paper for more details. So this is the overall idea of our result. So let me now conclude by mentioning two interesting open problems. The first one is that can we solve this problem in NC? So it was known that this problem can be solved in randomized NC. In this paper, we solved it in quasi-NC, deterministic quasi-NC. Can we solve this problem in deterministic NC? So the hope is that here actually what we do, actually we reduce this problem in some sense to PIT of non-commutative AVPs, for which we already have an efficient NC algorithm due to Ras-Vilka, and it is nicely mentioned in the PhD thesis of Forbes. The other interesting problem would be to obtain a heating set for non-commutative singular. So here the challenge is to come up with a list of matrix tuples H and S, N and S, two parameters, such that for any invariant sizes linear matrix, if it is invertible in the free cubic, there will be some matrix tuple in the heating set such that the determinant of the blown up matrix that we have defined, that will be non-zero. So what is known about this problem? If we only restrict each AI as rank 1 only, then from the work of Gurjar and Therev, it is known that this problem admits a deterministic quasi-NC algorithm. In black box, it has the deterministic quasi-polynomial heating set construction. Okay. In this paper, what we do, we consider another special case of this problem where the linear matrices are coming from rational formulas. So consider those linear matrices for which there is this corresponding rational formulas. And for that class of linear matrices, here we are able to construct a quasi-polynomial size heating set. The challenge is to come up with a heating set for the general case. Thank you.